Hello, I'm Dr. Sam Hancock of the Emerald Planet and Emerald Planet TV. We come to you on a week-to-week basis from Washington, D.C. in the United States as we look around the globe in 144 different nations, looking for those 1,000 best practices, the technology, services, and products that are making a difference as we move through the 21st century. And as we have a planet of 9 billion people by 2038 and possibly 12 to 13 billion by the end of this century, how are we going to be able to take care of all these people on planet Earth? And that's what Emerald Planet's all about. We come to you looking at the solutions, the best practices from around the globe as we create the Emerald Planet. Hello, welcome to the Emerald Planet. We're making a difference as we move through the 21st century. And seeing the long-term impacts of climate change. We're glad to have you. Thank you for being with us. Looking around the globe, and particularly here in the United States, the whole notion of sequester and rejuvenation, dealing with water, air, and soil. How do we improve these very natural ingredients that make up planet Earth, actually make up all of us living beings, whether we're animals, humans, microorganisms, or plants? And so how do we use all of this the best way possible? In our history, our legacy, of course, was very widespread mining all over the United States, particularly in the West, for every kind of mineral that was needed for the industrial state within the United States and for exports abroad. But now, how do we clean up all of this and make the Earth a better place in which to live and also to slow down climate change? Someone who's been doing several decades of research on this is here with us right now, Dr. Andrew Harley, who is the president, a researcher and author of the Ascension Soil Company. And we're going to be talking about rejuvenation of mine waste using both biochar and biomineral root stimulants. And Andrew, welcome to the Emerald Planet TV.
Thank you, Dr. Hancock.
Looking at this scene here as far as what we know from the old mine waste and where we're trying to go in the future to do this naturally and eliminate the harsh chemicals that we've been using for many decades now, particularly the end of the 19th century, moving into the 20th century. What are you finding out about how do we balance nature to heal itself?
So mine waste has its own challenges, and just like there are different minerals that come out of mines, whether it be gold or copper or iron ore or uranium or you know whatever it is. Though the waste that comes out of that material has its own characteristics as well. And up until fairly recently, the closure and reclamation process was engineering based. We will just take this material that can have pH issues. It can be very low pH to grow things. You can have high metal concentrations. You can have virtually no carbon or nutrients in these particular systems. So what we've done historically is we've just covered it with 3 feet of soil, or a meter of soil. We just throw it over and then grow on top of that, and we isolate it, or we dig it up and we put it into some form of repository. One of the exciting things over the last several decade really has been, how do we start moving from those what I call geological processes or geochemical processes and start moving gently towards soil forming processes, so we can go from these barren landscapes to these self-sustaining systems that can, just like any other system, can begin to cycle nutrients and carbon and water and these components, and begin to create these, again, self-sustaining systems using a natural design process.
I want to stay right here, Andrew, if you don't mind, looking at this image because it's such a stark contrast. But looking at biochar, biominerals, and using native plants, why are native plants so important into these areas across the West? But more and more, we're finding that we have the same issues just 200 years earlier on the East Coast and sometimes even in the Midwest of the United States.
So again, we're wanting to get back to that to what is the system that is most suited to that particular area and that particular location. And one of the things we look at in some of the disturbed sites, the photo on the left, is we always look for what are those plants that are actually naturally kind of colonizing these disturbed areas, and we're just looking for those local components. And again, as we begin to shift, because all landscape was disturbed at some point, and then there was this sequence, these colonizing plants, and then moving towards succession plants. And it's really, if you're trying to just plant the succession plant in a lot of issues out west right now deal with sagebrush and sage-grouse, and there's been a lot of work just trying to plant that sage-grouse, sagebrush, without going through that soil forming processes that then lead for this material to naturally come into to these sites.
Got it. Now, looking at this is a very complex image, but just kind of lightly take us through this, but give us the key points of what we're looking at and why this research that you've been doing for these last several decades is now really leading to this bioremediation. And if you don't mind if I add this, the biorejuvenation of these
Sure.
various soils and reclaiming these old mining sites.
So one of the things we're looking at, I mean, effectively, we see, whenever I start, I'm dealing with a, for want of a better word, barren or sterile environment. It has a certain chemistry to it. What we're trying to do is again understand what those processes that are going on at that time within that particular system, because there are still microbial processes going on, but they're designed for that particular chemistry, not necessarily plant growth. So understanding that and understanding what do we need to do, for want of a better word, to eco-engineer these soils, to understand what that process is by understanding what that microbial piece and that chemistry piece, how can we gently shift to move towards those soil forming processes. And again, we don't necessarily need to get to the final solution, but what is it that can then begin for the soils to take over and then naturally take over their components. So again, we're looking at, initially I start with, invariably low pH, low organic matter, low nutrients. What amount of material do I need to do? And just enough to begin shifting where that material goes, I can now shift and create this particular process. And so look at it at a staged approach. And sometimes it'll take several iterations until it becomes self-sustaining. But what we want to do is then get to that long-term stability within that system. Now, the challenge is that may take 5 to 10 years, as opposed to, well, we'll just come in and cover it, which is a short-term solution. But what we're looking at doing is that anything that you engineer, it doesn't matter whether it's a bridge or a slope or a cover, is most stable at the time that is built and will degrade over time. Whereas what we're looking at is creating something that is least stable at the beginning, but becomes more resilient and more stable over time. So this just really shows we're just trying to get those slow mechanisms that will eventually lead to that resilience and stability.
Well, the whole concept of this is it didn't get broken a day, it won't be fixed in a day. And so we just have to be patient with it. But most of these are very isolated areas. They've been totally degraded. And so anything that we can do that's going to improve it naturally is a wonderful process. What are we looking at here as far as this as a image of the natural process that we're actually looking towards and hope to be able to use far into the future?
So this is really kind of a snapshot of what I'm doing at any kind of actually on the ground. In that last photo. And what we're looking at doing is I'm looking at, okay, what plants can, and there are plants that can take up certain metals. So what are those plants that can take up those metals and begin taking them out of the system? What are those reactions that are happening in the root zone that will actually precipitate metals within the system? Then what are those bacterial reactions, and what's the bacterial population that is doing exactly the same thing? So again, beginning just to understand that process which again takes a little bit more time, but in the long run has greater stability. And I would also argue is actually cheaper in the long run. But it's again, sure. but again, it's just that it's that patience, it's that understanding that that we're not going to fix everything in a short period of time.
Now, this is something, again, it's very high and complex. What does this really mean to us? It talks about biochemistry, it's, bio everything. But how does this actually work together, the biome work together in order to bring long-term change and long-term improvement?
So effectively, this is just that, exactly that saying. This better describes that particular process that I'm working with. In state one, I'm dealing with this very unstable material. I've got materials that are highly reactive, are going to be leaching, producing acid, leaching metals. It's a very, very difficult piece. Stage two is where I'm really focused on at the moment. What do I need to do to begin to shift from that highly reactive, deleterious material to produce this intermediate step where I'm starting to get a degree of stability that then will begin to take over and create that third step, whereas it is functioning on its own without me, and will function on its own into the future without any further input from from human. Because as you pointed out earlier, a lot of these sites are remote, and they're very difficult to get to. They're very difficult to get material to. So they, whatever we can do to get those processes going. So it's really this just shows, I'm working really in that state two to move from state one to state three, to get from highly reactive to a biogeochemically stable system.
That's fantastic. I really like this chart. It is complex, but I think most of our audience around the globe will actually get this. But summarize what we're looking at here. Not all the chemical formulations. What is it that we're seeing, and why is it so important?
So again, this is where we need to understand what those microbial activity is going on. A lot of the material that I inherit or start with have these red, green, and purple material. Or sorry, really, so kind of the red material. It's just they're extreme bacteria that can just survive in very extreme conditions. What I'm wanting to do within the root zone, and then with the amendments such as biochar, is begin to figure out how can I create these safe environments, these localized safe environments for more plant growth microbes to survive. And this is where the root is important, and this is where amendments such as biochar is moving. So again, beginning to shift that microbial population away from those very extreme microbes that are effective in those environments to a more plant growth related system. This is where the roots are important. This is where amendments are important. This is where understanding what that piece is. And sometimes I'm actually adding in some of that beneficial bacteria to kickstart those populations as we begin to create systems that those extreme microbes are no longer needed.
And also, too, at the same time, Andrew, it looks like everything that you're combining here, as far as looking at the colors and what they're doing, is that you're trying to sequester water, you're trying to sequester carbon, you're trying to actually remediate the soil as this whole process, no pun intended, takes root and moves forward. But you're using all the elements of nature, the land, the air, and the water, because air is equally as important, oxygen right along with the water, to make these dramatic changes, but again, at a very slow, methodical process.
And I'm doing it in an isolated thing because a lot of these areas are large. And if you're trying to treat the whole area, that becomes very expensive. So what we like to try is targeting that process for, again, the process to take over on itself.
And allow it to expand on its own. Now we're starting to look at some of these areas. We're going to go through some of these images here, but just walk us through what we're seeing and what is the process that's going on, Andrew.
So this is just some dispersed tailings, a high altitude mine here in Colorado. We're at about 10,000 feet. So very difficult growing seasons. So short growing season, difficult terrain, and this is just the starting material that I was dealing with. You can see kind of the yellow patches within there that can show some of those extreme acidophiles that were low pH, high area. So this is just kind of no organic matter. So this is really kind of a very typical site of what I'm starting with.
Mm-hmm. Moving forward.
This is 12 months after we used this particular process. That's basically the same area. So you can see we're getting growth already, within the first 12 months by using this process.
I was going to say, when I was working on my 4-H projects as a youth, I was doing some of the things similar to what you have here, where you take dead trees that were in the area and then putting them out so it stopped the water. Slow down the flow, the erosion, and just let nature take its own. And it was amazing. Out of the 1,200-acre ranch that we had, we were able to convert probably several hundred acres over a 2-decade period doing this similar kind of process. So I can attest to the work that you're doing. The next step, Andrew.
And this was a couple of weeks ago, exactly the same area. So you can see, we're getting really, really good growth, stability. And so we're in a drought right now. This is low rainfall. This area hasn't received any moisture for over a month now, and we're still just getting that good resilient system that we're looking for. So that process has worked. Now we've got a couple of spots we may need to come back in and redo, but we've got pretty much 95% success rate on this particular area. This is 3 years later, and we haven't done anything else since that initial year.
Now, we were using trees that dead, dying, that we would actually take out and put in these areas again to slow down the erosion, the high water runoff when we did have severe storms. So tell us about these trees. And we see the grass is going up around the trees. Some of the grass, even at the trees, are much higher, taller than other areas. Why are these trees so important in this process that you have started here in this high mountain range?
So again, we're really looking at natural processes, and as you know, nature isn't flat and surface. So the concept we're bringing is kind of that I use in a lot of my sites is this concept of creating a rough and loose surface. So to create these micro topographies, these microclimates, these micro water retention areas. And again, I'm dealing in a very dry climate. So how do I better use water? So the trees, in addition to the water storage piece that you talked about, it's also a natural breakdown. We know that we're in a forested environment that the trees will break down just as trees do. So you think in a natural environment, trees fall down, they create these depressions where moisture can go and new growth can happen. But then they break down. They also break down and create those nutrients. So it's looking at that natural cycle, which is suitable for this forested environment in the Rocky Mountains.
And Dr. Andrew Harley, thank you very much as we look around the globe to create the Emerald Planet.